Welcome back to Chapter 4 of our ongoing exploration of the natural world. Thank you so much for joining me for this explainer. Today, we are setting the stage for just an absolutely incredible journey. We're going all the way from maritime folklore to modern physics and engineering. For centuries, the open ocean has essentially been a blank canvas for human imagination and honestly, human fear. It was this place where the unknown just kind of lurked beneath the waves. But as our instruments have grown sharper and our data has gotten way more precise, we've started replacing those terrifying myths with actual hard measurements. And what we're finding? Well, the truth is often much stranger and far more dangerous than the fiction ever was. Okay, let's dive into this. What really sinks ships in the open ocean? Because if you look back through centuries of sailor logs, maritime folklore is just packed with stories blaming the supernatural for ships vanishing without a trace. We're talking sea monsters, alien abductions, mystical vortexes, you name it, and a terrified crew has probably written it down in a logbook somewhere. But when we strip away all that supernatural stuff, we are left with a very real, very sobering question. When a massive vessel just completely disappears into the blue, what is actually happening out there? Let's look at one of the most famous maritime legends of all time, the Bermuda Triangle. We all know the popular myths, right? UFOs, or the lost continent of Atlantis just swallowing up ships and planes. But when we look at the actual data from the National Oceanic and Atmospheric Administration, the reality is heavily environmental. It's a highly trafficked area where the violently rapid currents of the Gulf Stream collide directly with these treacherous shallow Caribbean waters. You add in a heavy concentration of severe tropical storms and hurricanes, and you've got a recipe for disaster that requires absolutely zero help from aliens. Beyond just the weather, the ocean hides these invisible hazards that can completely confuse even the best instruments. Take magnetic declination, for example. This is a very real navigational hazard in regions like the western North Atlantic. Basically, it's the angle between true geographic north and magnetic north. In certain areas, a magnetic compass will actually point toward true north rather than magnetic north. If a navigator isn't perfectly compensating for this shifting discrepancy, their crew can be led miles off course. They could be steering directly into those shallow, reef-filled waters, or right into the path of an incoming storm. And, well, that brings us to the human element. A staggering percentage of marine accidents actually come down to simple human error, rather than any sort of mystical force. In fact, studies show that crew error on tugboats operating in narrow waterways actually exceeds 50%. When you're maneuvering a really heavy vessel through a tight, totally unforgiving space, tiny misjudgments in speed, or a simple communication breakdown on the bridge, or even just slight navigational errors are heavily, heavily punished. Now, this sensory confusion scales up to our next major hazard, which is spatial disorientation. Accident reports from aviation and maritime safety boards highlight this phenomenon all the time. When pilots or captains navigate into areas of minimal surface illumination, think like a pitch-black ocean on an overcast night, they can completely lose their sense of up, down, and where the horizon is. Their own cognitive and physiological senses just betray them. It's terrifying, and it really proves that the mundane reality of a dark, stormy night is so often deadlier than any myth. But let's pause for a second and flip the script here. We've just explained away a bunch of myths with mundane science. But what happens when the science of the 20th century is proven unequivocally wrong? What happens when a mythical sea monster, something sailors swore they saw but scientists dismissed as a complete mathematical impossibility, turns out to be absolutely terrifyingly real?
Enter the rogue wave. Now, by strict scientific definition, a rogue wave isn't just a big wave in a storm. It is literally a wall of water at least twice the height of every surrounding wave, and it appears with almost zero warning in the open ocean. If you're in 15-foot seas, which, is rough but manageable, a rogue wave in that exact same water can suddenly reach 80 to 100 feet. That's a 9-story building charging at you at highway speeds. And the most terrifying fact of all, they don't even need a storm to form. They can just ambush a ship on a relatively quiet day.
Now, people often confuse these with tsunamis, but they're actually almost exact opposites. A tsunami is triggered by a seismic event on the ocean floor, but out in the deep ocean, it's essentially just a long, fast, flat pulse. A ship in deep water would barely even feel a tsunami pass beneath it. The danger only really happens when that tsunami hits the shallow coast. But that exact same deep water, that is where a rogue wave becomes an absolute killer. The danger completely reverses based on the depth of the water. Mind-blowing, right? So, how did science finally catch up to this myth? Let's walk through the specific timeline of the Dropner oil platform out in the North Sea. On New Year's Eve of 1994, a low-pressure system formed. By early New Year's Day, heavy winds were churning the ocean, generating significant wave heights of about 39 feet. Basically standard rough seas. But then, at exactly 1524 UTC, a downward-pointing laser sensor mounted on the underside of the Draupner platform detected a sudden, massive anomaly passing directly beneath it.
And this brilliantly illustrates the turning point. 84 feet, 25.6 meters. That was the peak height of the wave recorded by that laser, and it literally changed maritime history in an instant. Before this single data point, standard ocean physics models classified a wave of this size in those specific conditions as statistically impossible. We're talking about something they thought might happen once every 10,000 years. But the laser didn't lie. The platform sustained minor damage, and science was finally forced to officially accept that these freak monster waves actually exist.
So how does the ocean actually pull this off? It really comes down to two main principles of wave physics. First up is constructive interference. Ocean swells are always traveling at different speeds and directions. Occasionally, as they pass through one another, their crests perfectly align and stack up, forming this towering, short-lived mountain of water. The second factor is the focusing of wave energy. When storm waves run head-on into a strong countercurrent, like the Agulhas Current or our old friend the Gulf Stream, the current dynamically squashes the wave frequencies together. This violently focuses their energy into massive, steep-sided rogue waves that can actually last for minutes.
Now, I want you to imagine you're on a massive 50,000-ton ship when one of these monsters hits. Your instinct probably tells you that a ship heavier than 400 blue whales can just muscle its way and push right through the water. But that instinct is dead wrong. A rogue wave doesn't just push a ship, it loads it. Think of holding a long wooden plank at both ends while someone just punches upward directly into the middle. The plank doesn't just move, right? It bends. The reality here is that longer ships are actually way more vulnerable because their extreme length gives the wave massive bending leverage right across the hull. To survive this incredible amount of force, naval engineers have to rely on some pretty counterintuitive tactics. First, the hull is literally designed to flex. Kind of like a tree branch in the wind, the ship undergoes what's called sagging and hogging, bending to absorb the force rather than snapping in half. Second, working alongside this flex are sealed internal watertight bulkheads. These ensure that even if one section breaches, the whole ship doesn't flood. And third, and this is just wild to me, captains must intentionally steer their heavily reinforced bows 10 to 15 degrees directly into the massive wave. Turning away would expose the broadside of the ship to rotational force, which would roll it permanently. You essentially have to climb the wall to survive. Well, once scientists finally knew what they were looking for, they went back and reanalyzed global satellite radar data to see if this Draupner wave was truly a 1 in 10,000 year event. And what they found was absolutely shocking. Rogue waves are occurring across the globe roughly 10 times a day. They had always been real, and they had always been frequent. We just never had the instruments in the exact right place at the exact right time to measure them.
Which brings us to a very sobering reality. Between 1969 and 1994, so that's the 25 years just prior to the Draupner laser recording, over 200 supertankers and container ships sank in the open ocean. Let that sink in. 200 massive vessels lost. And many of their causes were listed simply as unknown or just vaguely attributed to weather. Why? Solely because the very thing that most likely killed them didn't officially exist in the scientific literature yet.
So, the big question now becomes, how do we protect the seafarers of tomorrow? The answer definitely isn't building impossibly thick steel hulls. The future of seafaring survival relies entirely on making ships smart enough to avoid the threat completely. The next generation of protection includes satellite radar probability mapping, which scans the ocean in near real time. This data then feeds into AI navigation systems that can suggest course corrections hours before a ship ever enters a high-risk zone. Furthermore, live hull stress sensors feed flex readings directly to the bridge, letting the ship tell the captain exactly when it is approaching its structural limits. The ocean has thrown these monstrous waves at us for centuries. For most of that time, we simply called the survivors lucky and the lost ones a supernatural mystery. But now we finally have the tools to measure the myth and the technology to actually see it coming. So I'll leave you with this. If AI navigation and live sensor data can now predict the scientifically impossible, how will that change the future of humanity's relationship with the sea? Will the deep ocean ever truly be tamed, or is it simply waiting for us to discover its next great mystery? Thank you so much for watching this explainer, and as always, stay curious.